Hey, everybody, this is Mr. Lake live in studio with another instructional video. This time, we're talking about density. Let's talk about density. Let's get on with it. All right, so you've maybe heard the term density before. It's a very common word. It's informally, we often use density to refer to um, how compact something is. So, you like cake, for example. You might talk about a dense cake versus a light cake. And we're really talking about how condensed it is, how condensed that cake is, right? If there's a lot of if it's a flourless cake like a tort, it's not it's very dense. Whereas if it's a very kind of light cake like a angel food cake or something, then you would say it's not dense or it's very light. Well, density does have a more formal scientific meaning, which is it's the mass per unit volume. So it's how much mass is in a certain amount of volume for a substance or an object. Normally, the most common measurements, especially in chemistry, for density are grams per liter or grams per milliliter. Technically, density can be measured in any unit of mass over any unit of volume. So it could be pounds per liter or pounds per cubic yard, or it could be tons per cubic mile or whatever, right? But generally, grams per liter, grams per milliliter, sometimes kilograms per liter is what you're going to see it in. And this, up in the upper right hand corner, is the equation for density. Density is mass divided by volume, mass per volume. P is kind of the general letter that is used as a stand in for the term density. You might think, why isn't it D? Well, D is already used for other things like diameter and some other uh, variables. And so P is often what we use for density. Now, if you just write density or if you use D, it's not the end of the world. But oftentimes P is what we use. So let's cover this conceptually first. Different substances have different densities. Something like foam has a very low density. And that probably makes sense because if you have a foam pillow or a piece of foam, or you've ever packed with styrofoam, you can have a big piece of foam and it doesn't weigh that much because there's not very much mass per unit of volume. On the other end of the spectrum, something like steel is very high density. If you had a pillow sized chunk of steel, it would weigh a lot more than your pillow sized chunk of foam because steel has a lot more mass per unit of volume. It's a lot denser. It's really also important to remember that liquids have density, and in a liquid environment, things are going to behave a certain way based on their density. Specifically, they're going to kind of layer themselves in terms of density. So solid objects don't do this so much, but when you have liquids that are fluid, they will conform to the shape of their container, and they will also interact with one another and sort themselves by density. So on the left-hand side of this image are listed all of the different liquids that are in this image. And a lot of these liquids were colored in order to make them visible, right? So water, for instance, isn't green, but a little coloring was added to make it visible. Let's actually just use water as the point of comparison because everybody interacts with water all the time. We kind of know what it feels like and how dense it is and that sort of thing. So liquids that are more dense, like soap, milk, maple syrup, corn syrup, honey, those things have greater mass per unit of volume. And so they're going to sink below the water, and the water's going to float on top of those things. And if you're thinking about interacting with those substances, it probably makes sense. You're like, yeah, like soap is thicker than water, as is milk. Syrup is thicker than water or milk or soap. Honey is even thicker than syrup. Some people don't even think of honey as a fluid, but it is. It has fluid dynamics. So it is technically a liquid, but it's a very, very dense, very viscous liquid. Viscosity often goes along with density as well. You don't have to write that down, and it's not a perfect rule. That's not always the case, but generally, things that are liquids that are denser are more viscous, meaning that they don't flow as easily, right? They're thicker and goopier. Water has a low density, it flows really well. If you pour it, it just pours and it pours very quickly. Honey, if you try and pour honey, it's like, bleh, right? You've all experienced it. Honey is very viscous because it's very dense. So if we put some solid objects into a liquid environment like this, they also sort themselves based on density. So some things don't always just float or sink. Sometimes they will float above certain layers depending on what the density of the different layers are. So like a steel bolt is very dense, it's going to sink all the way to the bottom because it's more dense than any of the liquids in this environment. But a cherry tomato, it's more dense than water, but it's less dense than milk or syrup. And so the cherry tomato will kind of float right in the middle. And the ping pong ball, which is mostly air, is very has a very low density. It's less dense than all of this stuff. And so it's going to float on top. So if you've ever wondered why something sinks or floats, it's all based on density. And technically, it would be possible for something to float in the middle, especially if you have a couple of different substances present, like liquid substances, and the density of that thing is right in between them or right in the middle of that kind of range. So now you know why stuff floats. Interesting to think about. But of course, we are going to take this to a mathematical level because that equation for density is something that we can use to solve problems. We'll start simple. We'll just calculate density. Let's say we pick up a rock, put it on a scale, and it weighs 50.0 grams. And we find the volume of that rock, and it's 8.5 milliliters. So, what's the density of the rock? Take 30 seconds and solve this on your own. Okay, hopefully you pause the video and solve this. I'm going to come back and show you how it's done. The equation for density is density equals mass over volume. Looking at what we've got, we know the mass of the rock is 50.0 grams, and we know the volume of the rock is 8.5 milliliters. So all we have to do is plug those numbers in, 50.0 grams over 8.5 milliliters. And if we solve this using our calculator, 50 divided by 8.5, we get 5.882. That's our answer. Or is it? There's a couple things wrong with this. What are they? Well, number one, it's missing units. We've got to have units on every number. So, what are going to be the units of density in this situation? Well, our mass was in grams, our volume was in milliliters, so our density is just going to be in grams per milliliter. The other thing that you may have forgotten about, but I'm going to remind you now, is significant figures. We have to think about significant figures anytime we do a calculation. When we divide numbers, remember that the answer that we get can have a number of significant figures equal to the original number with the least sig figs. So if we look at our original numbers, 50.0 has 3 significant figures. 8.5 has 2. That means we can only have 2 significant figures in our final answer. So we can keep the 5, we can keep this 8. Then we have to look at the next number to see whether any rounding happens. The 8 is followed by another 8, so rounding does happen. And the actual answer, the way we should report this, is 5.9 grams per milliliter is the density of this rock. Obviously, 5.882 is a good answer because it's numerically correct, but 5.9 is the correct answer because it also has the correct amount of accuracy for this particular situation because of those sig figs. Now, I just gave you these numbers, right? Mass and volume. But in an experiment, you're going to have to figure them out. And the most common way to figure out volume, mass is easy. You just put it on a scale, right? If you've got a working scale, put the object on a scale, it'll give you the mass. Volume is trickier because most things aren't convenient shapes. If you just had a block of something, you could measure length, width, height, and just multiply them together and you'd get the volume. But if you're measuring, say, a rock isn't a perfect square, usually. It's got crevices and it's got protrusions and it has holes and divots and all these things that like you could never use a ruler to get a good volume for that rock. The best way to do it is by displacement, meaning that you have a volume measurement tool like a graduated cylinder that you put some water in, some certain amount of water. It's going to differ depending on the situation. And then you put the object into that water so it's completely submerged, it's underneath the surface of the water. The level of the water is then going to rise. And the amount that the water level rises is the volume of the object because the object is displacing the water. So, like in this situation, we have a rock, we put it on a scale, we know it weighs 25 grams, so that's the mass. But then we don't know the volume until we put it in water. So we're going to place it into a graduated cylinder that has 20 milliliters of water in it, and the volume of the water goes up to 20 to 40 milliliters. So what's the volume of the rock? Well, it's going to be the volume of the rock plus the water minus the volume of just the water. So rock plus water was 40.0 milliliters. The water was just 20.0 milliliters. And so that means that the rock, that's not right. 20.0 milliliters is the volume of the rock. It's our volume. So now we have what we need to calculate density. Density equals mass over volume, 25 grams over 20.0 milliliters. 25 divided by 20. The density of the rock is 1.25. Again, units and significant figures. We have to pay attention to those. For units, we had mass in grams, volume in milliliters, so units are going to be grams per milliliter. Significant figures, this number has 2, this number has 3, so we're going to keep 2 in our answer. The 1 and the 2. Then we look at the next digit to follow it. It's a 5 or greater, so the 2 is going to round up to a 3, and our density should be reported as 1.3 grams per milliliter. Cool. I hope that makes sense. Density, like any equation, can be used in any direction. So we aren't only able to calculate density, we can calculate other things using the density equation. For example, if you have a sample of something that you know the density of, and you can measure one other thing about it, like maybe you can measure its volume, but you don't have a scale, so you can't measure its mass. Or maybe you have a scale, so you can measure its mass, but you don't have a good way of measuring its volume. You could calculate what you don't know. So if you know density and mass, you could calculate volume. If you know density and volume, you can calculate mass. It works you can use that same equation to solve for any one of those 3 variables as long as you know the other 2. Here's an example. And I would like you to pause the video and give this one a try. So I'm going to stop talking for 5 seconds, pause the video, press start once you've given this a shot. Okay, if you haven't paused yet, pause it and make sure to try it on your own. Don't just watch me do it. But if you have tried it, let me show you how this is done. We have a metal bar. We know the density. Whoops. Oh, I get it. Sorry, took me a second there. Okay, we have a metal bar. We know they changed the controls on this program since the last time I recorded a video, so I'm getting used to these new changes. Sorry about that. We know the density is 7.9 grams per milliliter. We also were able to figure out that the volume of the bar is 500.0 milliliters, and we want to know mass. So we're still going to use this equation. Density equals mass divided by volume. We know the density, 7.9 grams per milliliter. So we can plug that number in. We don't know mass, so we're going to leave that as a variable. And we know the volume is 500.0 milliliters. So to solve for mass, we're going to cross multiply, right? You can either think of it as we're cross multiplying this numerator times the denominator on the other side, or if you like to think about math at its root, what we're really doing is we're multiplying both sides by 500 milliliters. Because that's how we get rid of 500 milliliters in the denominator on the right-hand side. And that would leave us with mass equals 500 times 79, sorry, 7.9, 3,950. Units are going to be in grams. That's a pretty good answer. But we still have to think about significant figures. And the significant figures in this situation are a little bit tricky. So this number has 4 significant figures. This number has 2. That means our answer can only have 2. Our 2 significant figures are the 3 and the 9. But the 9 is followed by a 5, meaning that it is going to round up. And when a 9 rounds up, it rounds up to 10, and so it rounds up the number before it. So what this number is really going to become is 4,000 grams is equal to the mass. But this first zero is significant. This number looks like it only has one sig fig, but actually the first zero is significant. There's a couple ways you can indicate that it's significant. One is to write a line above that zero, and that says that this is actually the last significant figure. But I think the way that I prefer would be to switch this to scientific notation and say that it's 4.0 times 10 to the third grams. That tells you that there's 2 sig figs, the 4 and the 0, and it gives the number, and there's not really any confusion about how that works. So this should be our answer. Whoa, what's going on? That should be our answer. I also want to point out that some people like to rearrange before they punch in numbers. So if we have this equation and we know that we're going to solve for m, instead of putting the numbers in and then having to do all the calculations with numbers in there, we could just rearrange it beforehand. So if we know that we want to solve for m, we want to get m by itself. So if we cross multiply density times volume, we get that density times volume equals mass. And that's a little bit easier because then you can just, plug this number in here, plug this number in here, multiply them, and you've got the mass. You don't have to do all of this stuff here, right? I'm happy with it either way. I think you should figure out what works better for you. Are you a rearrange the variables and then solve person, or are you a put the numbers in and then move things around and get to your answer? I tend to put numbers in, even though I know it's less efficient. For some reason, I tend to just put the numbers in. But sometimes, especially when things get more complicated and we get to bigger equations with more variables, rearranging so that you already have isolated the variable you're solving for can save you a lot of time. Holy moly, I went into a bunch of extra stuff on that question. That wasn't even just like an instructional little bit on density. That was like significant figures, units, rearrangement of variables. Hopefully I made some sense. There is one more problem that I would like you to challenge yourself with. So please pause the video, take a few minutes, solve this problem as best as you can, and when you're ready, hit play and I'll explain how it's done. Okay. So we're talking about bowling. And let's say that you know that you bowl best with bowling balls that are less than 5,300 milliliters in volume. But that's kind of a difficult thing to just eyeball, right? Volume, especially of non cubic things, is a hard thing to just do in everyday life. I also want to point out that knowing that you have a specific volume of bowling ball that you prefer is kind of a weird thing to know about yourself. But anyway, let's not question the question that I wrote. Why would I do that? Let's say that you also know that the density of bowling balls is usually around 1.36 grams per milliliter. Again, why you would know that, I don't know, but I wrote this question, so we're going to keep going with it. So you go to the bowling alley with some friends. You grab a bowling ball off of the shelf and you put it on a scale, and it weighs 7,143 grams. Based on what you know about density, is this the right volume of bowling ball for you? Weird question, but I'm kind of weird, so that makes sense. So we know, first of all, that the mass of the bowling ball is 7,143 grams. We also know that the density of the bowling ball is 1.36 grams per milliliter, because that's the general density of most bowling balls. That is a real number that I got from the internet. I think it's bowling balls have a density between 1.32 and 1.36 grams per milliliter, generally. If you want to remember that, go for it. What we want to know is volume. So we've got density equals mass over volume. We are going to solve for volume because we know density and mass. So let's actually do the rearrangement thing ahead of time. All right, we're going to cross multiply density times volume. Density times volume equals mass. But we want to get volume by itself. So now we're going to divide both sides by density, and we get that volume is equal to mass divided by density. So now we just plug in our mass, 7,143 grams. We plug in the density, 1.36 grams per milliliter. And we get that the volume, once we plug it into the calculator, is 5,252.205. And again, units and significant figures. This volume is going to be in milliliters because the density that we've got here is in milliliters. And what's going to happen if you're paying attention to the unit math here is that grams cancels out because you've got grams over grams, milliliters, since it's divided by grams per milliliter. Milliliter is technically in the numerator. And so anyway, the easier way to do this is just look back at your numbers and think, oh yeah, milliliters is the volume unit we're dealing with, so the volume must be in milliliters. Now, significant figures. This number has 4. I'm going to use a different color. This number has 4 significant figures. This number has 3, and so we only get to keep 3 significant figures. It's going to be the 5, the 2, this 5. So we're going to drop all the other significant figures. We know we're going to need a placeholder 0 here. And we also are going to look at it to see whether any rounding occurs, which it does not because it's less than a 5. So volume in the end will be 5,250 milliliters. So to answer the question, yes, this is a great bowling ball for you because you like bowling balls that are less than 5,300 milliliters in volume, and this one indeed is less than 5,300 milliliters in volume. So you're going to have a good night. Get lots of strikes and spares. That's what you want in bowling, right? Who am I kidding? I know how to bowl. All right. Thanks, everybody. Until next time, have a fantastic one. I'll see you in the next video.